Hello, I'm Richard with EV4U Custom Conversions, and welcome to another edition of the EV Answer Man. In this episode, we're going to discuss the Yamaha Rhino again. We're going to look at the feasibility of converting it to electric, and specifically we're going to look at the gear ratios and see if this is going to work with what we have planned. So let's go out to the Rhino and take a look at what we're doing. Okay, here we are with our 2006 Yamaha Rhino, and what we've done is we've made a mark on the tire and on the ground to measure the distance in 1 revolution. We've also marked a mark on the front differential, actually on the front universal joint there, put a piece of tape so we know when that comes around 1 revolution. We did the same on the drive shaft. And so what we're going to do is we're going to rotate the tire 1 revolution, and then we're going to monitor the distance traveled and the revolutions on the drive shafts. The drive shafts should be the same. That would be the assumption, but we'll find out for sure. Now's the time to know these things, not after we've assumed that it's going to be a certain way and find out later we were wrong. So, I'm going to push this forward and keep an eye on things and see what happens here. Okay, that's 1 revolution of each of the drive shafts, or it looks like a 1/4 revolution of the tire. Well, it appears to be 4 3/4 revolutions. That's where it ended up on. It's kind of about the 1 o'clock position there, and about 12 o'clock position there, and we made a full 360 there. So let's measure and see what distance that was. Looks like 75.5 inches. Okay, there's the tape on the drive shaft, and so as we rotate or move the vehicle forward, you'll see it rotate. And so you can see that it rotates if I'm viewing from the motor end, when the motor would be in the middle of the vehicle, then it is rotating in a counterclockwise direction, which is perfect. That's the direction our net gain motors like to turn. And so counterclockwise at the drive end is what we want. One of the things that is observed, let me see if we can zoom in here a little bit, is the clearance there. There's a cross member, and then the frame and everything is, or the belly pan, it's pretty close. This drive shaft is really low, and the way it exists is here's the rear brake disc, which is mounted on the drive shaft. And so as the drive shaft has no universal joint, we would have to be dead on. So I think we'll probably make up a drive shaft and do it in such a way that we raise the motor up a little bit. But we'll see. When we get to that part of the engineering, we'll see what we need to do. So anyway, we know direction, we know the ratio, and so let's go to the board and to the calculator and see if this all works out with our motors. Alright, so we made our observations and we observed that it was 3 3/4 revolutions to 1 of the tire. And this is drive shaft. Okay, and we know that, if my memory serves me correctly, that there's 5,280 feet in a mile. And so we did our measurement in inches, so let's do it in inches, so that would be times 12. Okay, will give us the number of inches, which comes out to be 63,360 inches per mile. And 1 revolution of the tires was 75.5 inches. So we're going to take that 63,360 and divide that by the 75.5. And that gives us the number of revolutions per mile for the tire, which is 839.2 revolutions per mile tire. And so we also observed that there was, the 3 3/4 revolutions for 1 of the tires. So we're going to take the 839.2 times 3.75, and that will give us the revolutions of the drive shaft per mile. And that was 3,147 revolutions per mile. Or if we do that every minute, that would be revolutions per minute. So going a mile a minute, that would equal 60 miles per hour. So this many revolutions of their drive shaft equals 1 mile. If we did that in a minute, we'd go a mile a minute, which would mean we were going 60 miles per hour. And so that's a nice number. That's the net gain motors, typically 32 to 3,400 RPMs is kind of the sweet spot. And that would be great. But I've ridden in the Rhino many miles, and I can tell you 60 miles an hour is way too fast. We have to think about the other end of the spectrum, low-end torque. Of course, we all know electric motors have great torque at the low end, maximum torque or almost maximum torque at 0 RPMs. But this stock Rhino had a maximum speed of about 38 miles per hour. Miles per hour max. That was stock. And ours has been modified. It'll do 41, 42 miles an hour. And that's plenty fast. And that's much faster than you normally go on most terrain if you're off-roading. And that's what that vehicle's best suited for. So, what we would probably want to do is put something into place to actually increase our RPMs so that we would be doing this number of RPMs at, say, 30 miles an hour. So, you know, you could go with a smaller tire diameter and things like that, but we don't want to do that because we don't want to decrease the ground clearance. And that's also a real nice size rim right now. It's a 12-inch rim. Don't want to go any smaller than that. And so we will probably come up with a reduction method, which also might work well with the fact that we observed that the drive shaft is in close proximity to the belly pan. And so we don't want the motor touching the belly pan and so forth. So what we'll be able to do is do a gear reduction. You have twice as many teeth on one gear as you have on the other, and we'll get our 50% reduction. But we know a starting point now. We know that the gearing of the differential is a little high. I don't know if it's possible to change that gearing. I think probably the easiest fix overall and it would be to leave that drive shaft pretty much the way it is, set it up so we can have a gear reduction, keep that shaft stationary the way it is right now, and then have another gear off the motor. And so this looks like it's doable, looks like it will work. But it gives you an idea when you're converting something that you know, no one's done before and you really don't have any insights, you have to do all of the engineering. We have to figure out what is doable, what's going to need modification, and so we've now figured out pretty much what we need to do on the drive ratio, and that is we'll put a 50% reduction in our final drive. So when our motor's doing approximately 3,100 RPMs, we'll be doing 30 miles an hour, which is beautiful. And we still have enough to take that Rhino much faster than the original one would run. This one would probably be able to do 50 miles an hour or better. And so everything looks good. I don't know what the original horsepower and torque specs are on that. The original motor is a 421cc single cylinder, but I looked through the book. Nowhere does it say what the horsepower or torque rating on that is. So that's it for right now. Let's go do one other thing, and that is a while back we replaced the brushes on our Karmann Ghia. The brushes that came in it were really not the correct brushes for the motor, and they looked like they had put two different brush sets in there, in that we had 4 of them wearing at one rate and 4 running at another, and you can check out that previous video. So the replacement brushes have been in for about 2,000 miles now. I was told that they would have a 3,000 plus mile break-in, seating time, and so we've run them now for a while, and so let's take a look. I want to check and make sure everything's going the way it should. The issue with this one is that we're running a blower motor on it, so we have a band over the commutator end, and we can't see these without removing it. So I don't know at a glance what's going on. So we'll pull the blower motor off and remove that band and take a look, pull one of the brushes out. We'll pull several of them out. So let's go out to the shop and take a look at the brushes. Well, here we are in the engine compartment of the Karmann Ghia. Here's our motor, this is our blower, and so to check the brushes we need to remove this, and so we'll pull the blower off and remove that band and take a look at them. So need to remove these cables to do that. So we'll pull those off first, get them out of the way. I already threw the main circuit breaker as a safety precaution so that we don't have any potential to get shocked. I don't like surprises, so we try to play it safe. Okay, now we need to loosen up the band underneath here. And so you can see it's not a real involved process. It takes just a few minutes. While we're in here, we'll also blow off the brushes and blow out the motor. Probably should have checked this sooner at 1,000 miles. But everything's looked very good, and as far as the amount of dust coming out the fan end, and since everything looks so good, we just let it roll. Plus, this car seldom misses a beat. I mean, it's being driven all the time. We now have over 7,000 miles on this since July 1st, so it's driven quite a bit. Okay, there we are. Looking at the brushes, everything looks very nice. They all look like they're wearing the same this time. Much better than before. And so, let me pull some of these out and we'll take a look at the mating surface and see how they're wearing. Okay, removing the little bolt screw that attaches the brushes here. Use my little tool to remove the spring, lift the brush out, and there we have it. And I'll see if I can get this to show up on camera, but we still are only running about maybe 75% contact area. And so I brought some of the old brushes to compare. And so lengthwise, we've put 2,000 miles on these versus 3,000 on the others. I don't know how. There was the ones that were wearing the best. That's the difference between 1,000 miles. So these are a harder brush, wearing much better. Contact area, I'd say, is getting better, but we're still not there. You can see area that is not actually making contact yet. And so I see where these are going to take at least 3,000 miles. Here's the other brush that was in there in the original setup, and that was the difference in the same number of miles between brushes. So, and again, the contact area, either it doesn't look like it was contacting very well, so I was probably getting 50 or 60% contact on these. That or that might be pitting. You know, with the naked eye I can't be sure. I'd have to look at it under magnification. But this one I'm sure that we're not making contact yet. And where it is, it's a nice, smooth, beautiful. And the platina on the motor, beautiful. Much better than it looked before. And it looks clean in here. I don't see a lot of dust. This is beautiful. I'll try to get a close-up with the camera here and see what we can see on camera. Here's the close-up of that brush. You can see in the top part that it's not wearing there yet. We haven't made full contact. So once you start making full contact, that will be the ability to have good power draw through these brushes. So I'll take a peek at some others and see how they compare. But let me see if I can get a camera shot down in there of the commutator for you. So let's pull it off the tripod, move in here for a close-up. Boy, can you see how shiny the commutator is? You know, it was a kind of a dull copper color before. Boy, with these new brushes, it shines. Oh my word. Really, really shiny down there. So anyway, the good news is that they're wearing the same. You can see how they're the same length. whereas the previous ones were wearing differently. The outboard ones were wearing at a different rate than the inboard ones. This time everybody's wearing the same, which is what you would expect. And nice platina going on the commutator. And we're off to a good start on the wear on the brush. So it's getting there, but where it is making good contact, it's a very smooth, nice look versus the original brushes. You can see where it was making good contact, and even there it wasn't, it has some pitting. And so definitely at the voltage that we're running, which is not real high voltage, these harder brushes are supposed to be good for higher voltages. We're running at kind of a, maybe what I'd call a mid-range voltage, 146 volts. We're not up there in the 300s where a lot of them like to run. And so I'm pleased with this brush. This is what George Hamstra recommended, in which he sent to me as a free replacement. So that's another nice thing about NetGain Motors, is they got great customer service. We are a dealer, but I don't think that matters one iota. I think they take care of all their customers, and so we're very happy. This is the first issue we ever had with a NetGain motor, and this is kind of a transitional motor. It was the first one we received that had the red top Hellwig brushes in it, and so, and they make changes all the time. They're continually improving their motors, and that's just a very nice setup that they have. And so if you want a DC setup, this is the motor we recommend. It's the motor that we use ourselves, and it's a good motor. This is the Impulse 9, which we run in the Volkswagens because of the difference in length between that and the Warp 9. Warp 9 is a little too long, won't fit in our engine bay without cutting some sheet metal, which we don't like to do. And where you have to cut it's where the latch goes. So not our way to want to go. If you want one that way, we can do it for you. But our recommendation is on the Volkswagens, either go with the AC50 AC drive, or with the Impulse 9 for the DC drive. So I'm going to take a look at some other brushes and see how they look. I expect they're going to look exactly the same as this one. So until next time, I'm Richard Van Wahy with EV4U Custom Conversions, and if you have any questions, feel free to contact us at info@ev4unow.com, or check us out on the web at ev4unow.com, and we'd be glad to help you convert your own vehicle or do it for you. See you next time.